Hi, I'd like to show you the problem radio commercials. Okay, this problem is a version of what we call a maximum subarray sum. Okay, so in this particular problem, the setup was such that we were given a sequence of numbers, and these numbers represented some benefits to be had if one particular point is selected. But there was a cost that you had to subtract from these numbers. So after subtracting this cost here of 20, the resulting sequence actually was something like -2, 15, -14, 60, -5, and then 1. And you were asked to find a subarray in here, a contiguous subarray, such that the sum of these numbers was maximized. And so here in this particular example, the answer I think was 61, and 61 was obtained by, in this case, selecting starting here, and so this would be 15 negative, so this is 1, and then stopping here. Okay, and the sum from here to there is 61. If we extended it to here, it would have been 56, and then here with the 1, 57. So this is really the optimum. So so we don't want to include this, and we also don't want to extend further. Okay, so this is a classic problem, and it's got a relatively simple solution. Here are the insights that you need to know. So number of insights. The first one is that the problem only makes sense with if you have positive and negative numbers in the array, right? If all numbers are positive, you just take the entire array, and if all numbers are negative, then you would select a zero section of the array. The second is that the optimal solution here in this one clearly does not have a prefix with a negative sum. Okay, so what cannot happen is that the optimal solution here, that there is some prefix here where the sum of these elements is less than 0. Because if this were the case, then we could just cut it off, and then we would have a better solution in here. So the optimal solution does not have a prefix where the sum is less than 0. And then the third insight is if you consider the following: if you go through the array and you say at this element at I, okay, so if there is an optimal sum of a subarray here in this case that ends at I, okay, then you can use this information to compute the value of the optimal sum that ends at I plus 1 here. And this is simply the sum here plus a of I plus 1, right? Because you're adding this to it. But because the prefix here cannot be negative, okay, it is either that or it will be 0, right? And these insights allow us to perform the search for the optimal subarray sum in a single pass. Okay, and we'll show you how to code this. This is a well-known algorithm referred to as Kadane's algorithm. Okay, so here in this case, I'm going to write this in Python. The input has the first line is n and p. P is this cost that we need to subtract. And so if we read this, and then the actual values of the array, I'm going to call those a, are then followed. And then so we simply go through all the values in the array. Okay, we need to keep track of two things. We need to keep track of the best so far, okay, and then the best total. Okay, because as we go through the array, what can happen is, right, we keep track of the best one that ends here, the best one that ends here, and so on, right? But it may be possible that there's negative numbers here, and the best one is actually earlier. So we need to keep track of the best overall as well. So we're going to best overall. Okay. So we're going to go through here. I'm going to say the best so far, okay, is the larger of the best so far plus adding this new element in here. This new element is a, but we have to subtract this cost p. And then otherwise it is 0, because we do not want to have, there's no point in considering negative prefixes. And then the best overall here is the maximum of what we believe the best overall to be so far, and best so far, right? And then at the end, it's asking us to output the best overall. So if we test this here, we get the answer 61. And let's see if we can submit this. And we see that it was accepted. So this again, this is referred to as Kadane's algorithm, and it is a nice little idea of how to that allows you to find the sum, the optimal sum of a subarray with positive and negative numbers, and the complexity of this is O of n. Because it relies on extending the optimal sum that ends at one point to the next one, it is also known as an example of what we call 1D or one-dimensional dynamic programming.